Relativity seminar. It's our pleasure to host the Ilkka Mäkinen, who was the postdoc, who was a PhD student and postdoc with our group, and now he is a postdoc and NCBJ, but he will come. He came here to give us talk of his recent work on loop quantum gravity in diagonal gauge. Ilkka.
Thank you very much. So, the plan of my talk is here. So I'll start by giving a very quick introduction to loop quantum gravity, or maybe a reminder, depending on how much you already know. And after this, I go to the main part of the talk, which is loop quantum gravity in diagonal gauge in some sense. So I'll define a constraint operator in the quantum theory, which represents the gauge conditions that I want to impose. Then after this, I derive some solutions of the constraint, and this part of these solutions are not exactly anything new. They are already known in the literature, but maybe this method of obtaining them that I'm going to present here is different than before. And after having this space of solutions, I will study how the operators of loop quantum gravity act on these states, and this result is, as I'll explain later, it's kind of nice, and it, from the technical point of view, at least, is the main motivation why I find this type of model interesting. And in the end, depending on how much time there will be, I will comment briefly on some ways of generalizing or extending the construction, and then finally I'll of course summarize and give some conclusions. Okay. Right. So what loop quantum gravity is basically is a canonical quantization of general relativity, but expressed in the Arstekar formulation. So this is, of course, a canonical formulation with a 3+1 splitting. Then on the spatial surface, the elementary canonical variables are the Arstekar connection and the densitized triad. And then this, of course, as is to be expected, this a fully constrained formulation. So you have this, well, as in the ADM formulation, for example, you have the diffeomorphism and Hamiltonian constraints. And here in the Arstekar variables, you also have the Gauss constraint, which corresponds to the fact that you can make internal rotations of the densitized triad while not changing the spatial metric. And then to pass to the quantum theory, or to quantize this formulation, you cannot directly use the connection and the triad, since these are sort of not very well behaved if you try to turn them into operators. So what you use instead are these sort of smeared variables, namely the holonomy or the parallel propagator of the Arstekar connection along some curves in the spatial manifold. and the fluxes of the densitized triad through two-dimensional surfaces. Notice that both of these things are like naturally defined without having to use any arbitrary background structures like a metric. So from the mathematical or conceptual point of view, one of the main ideas of loop quantum gravity, the one that makes it different from a
very stupid question.
go ahead.
Yeah, I use almost the same definitions. However, in my definition, there is factor of 1/2
Yeah,
here. And I'm wondering whether you systematically use this definition with this factor.
no, I looked at it like this introductory slide. There might very well be a 1/2 missing.
I mean, there's usually this difference in your formulation.
There is a different assumption about the wedge product. Like you can define wedge product with the different factors.
Well,
So what is your definition of the wedge product?
well, it's the same as yours, but I agree now that if I was completely precise, there should be a 1/2.
On the other hand, this difference doesn't have any consequences if you systematically take this consequently take it into account.
Yeah.
Because then you just in different way, you just take it into account.
Yeah, but I agree with what you say. If I was doing something precise with this, I should put there 1/2. Which I mean, the reason I guess why I forget it is I don't normally write it in terms of the wedge at all. I mean, write some normal vector on the surface and
Usually you don't have summation, but you already have one specific there.
yes. Okay. So what I was saying is that this important feature of loop quantum gravity, you can already see here that it's the quantum theory is to be constructed without introducing any fixed background metric or any other structures like that. So it's a background independent quantization, and this is the main feature that makes it very different from some conventional quantum field theories. Okay, so then
just to make sure, so in this case, you're working on a fixed Cauchy slice, right?
yeah, these variables are on a fixed slice.
Okay,
yes.
so in particular, you don't allow any topology change.
No, at least at the classical level, no. In the quantum theory, I'm well, if it somehow happens there, then I don't know, but
Okay, thanks.
yeah, but at least at the classical level, everything is on a fixed spatial slice with a fixed topology, and there's no such things like topology change. Okay, so in the quantum theory, the kinematical Hilbert space is spanned by these so-called spin network states, which have this structure. So first of all, a spin network state is labeled by a graph embedded in the spatial manifold. And each edge of the graph carries a spin or an SU2 quantum number. and in the wave function of the state, there's a SU2 representation matrix associated to each edge. Then if there are n edges of the graph, then the wave function is a function of n SU2 group variables. Then at the nodes of the graph, there are some intertwiners or SU2 tensors. This dot in the middle means contraction of the magnetic indices. So the indices of the Wigner matrices are contracted with the indices of these intertwiners according to the pattern that can be read off from the graph. Physically, what a state like this describes is a discrete quantized spatial geometry. So at each node of the graph, there's a quantum or a discrete element of volume. If two nodes are connected by an edge, then it means that these two pieces of volume are sort of next to each other, and there's an elementary quantum of surface or area in the middle separating these two. So this is essentially a theory of quantum geometry. So the idea somehow is that if classically gravitation is a geometrical phenomenon, then a quantum theory of gravity should be a theory where geometry itself becomes quantized. And in this way, quantum gravity gives a sort of concrete realization of this idea.
Yeah. In general, would be good to notice at this point that many people think that not only geometry should be quantized, but manifolds should also be quantized. And so what this is an important certainty that one possibility is that manifold is given like everywhere in all physical theories and would be quantized in quantized fields, which are metric tensor. And this is what we do in our approach to quantum gravity. But some people even want everything to be emerging from quantum theory, including space-time. So some people introduce some abstract states, and then they give some prescriptions how, or usually don't give, but they look for prescriptions how space-time also emerges. They think it's fair to indicate that even if we don't do it, this is another option.
Yes, it is true that so it is possible to do this, like starting from this picture that I show here and forgetting everything about the classical manifold, and then this would be some kind of abstract graph not embedded in anything. And it is also well, it is a different point of view, but as you said, it's also something that many people do. Okay, so then here for later use, I show how this. So on the previous slide, I had the classical holonomy and flux variables. Then here for later use, I show how the corresponding operators act in the quantum theory. Well, first, the holonomy operator here, even though I put a hat to show which of them is the operator and which is the state, is just multiplication of the SU2 matrix elements and is given by this well-known Clebsch-Gordon series. So here these C's are just the usual SU2 Clebsch-Gordon coefficients. Then the flux operator. So here there are many different versions of this formula depending on how the edge E and the surface S are located with respect to each other. But here, to give just one example, I'm assuming that the starting point, so it's an oriented edge, and the starting point is on the surface, and in this case the flux operator acts like this. So here this tau is up to a numerical factor, is just the generator or the Pauli matrix. So this flux operator, its action is very similar to the simple angular momentum operator of quantum mechanics. And there are also further operators like geometrical quantities such as areas and volumes and so on. And I will just mention this here. So now if I was continuing to give a lesson of loop quantum gravity, the next thing I should say is to describe how the constraints are addressed in the quantum theory, like the state of or space of state solving the Gauss constraint and the diffeomorphism constraint and so on. But I let that be, and I'll just say that the current status of this formalism, so to say, is that from the mathematical point of view is extremely nice and solid, and things are quite well defined. But from the physical or practical point of view, it's quite difficult to extract any concrete physical consequences of this formalism, which of course in any approach to quantum gravity is a problem, because there are not many accessible physical phenomena where quantum gravity would be relevant. But in loop quantum gravity, even in principle, it's quite difficult to calculate anything just because of the technical complexity of the formalism. And because of this, people have tried to develop some simplified approaches which are more manageable, but still in some way at least related to the full loop quantum gravity theory. Now, one possibility is to do a classical symmetry reduction. So you assume that for example, that the metric is homogeneous, or the geometry described by the metric is homogeneous and isotropic. Then this already at the classical level, it reduces the infinite number of degrees of freedom to just one, which is the scale factor. So then you quantize this system with 1 degree of freedom, and this basically what loop quantum cosmology is. Of course, there can be anisotropic models, or there are also models of spherical symmetry like this. So it can be more than 1 degree of freedom, but it's still a very drastic reduction already at the classical level, which you do in this approach. Another possibility, which is the subject of my talk, is to use gauge fixing to try to construct your simplified model. And I'll specifically be interested in this second option here, which is that you classically don't do anything. You quantize the full theory in the way that I just showed. Then after this, you do something in the quantum theory, which you argue that can be interpreted as a gauge fixing. Specifically, you construct a constraint operator such that this operator being 0 can be argued to represent the gauge conditions you want to impose. And then this operator selects some subspace or some sector of the entire Hilbert space of loop quantum gravity. And this basically is the model of quantum reduced loop gravity, which already is known in the literature and was introduced by Alesci and Cianfrani. So this structure that I present here is not exactly anything new. If there's something new, some new contribution in this talk, then it will be that my way of deriving this model from the full theory is possibly more systematic and more clear than what these people originally were doing. And there are, of course, also many other approaches to the problem of extracting physics from loop quantum gravity, not all of which can even fit on my slide, but here I included one more. Okay, so let's first think classically how works the gauge fixing that I eventually want to do in the quantum theory. We have the densitized triad, which it looks like it has 9 independent components. However, there are the 7 constraints, and then after the constraints are imposed, the number of degrees of freedom is reduced to 2 per point, as we know it should be. However, what you can do is you can take the 3 diffeomorphism constraints and the 3 Gauss constraints, at least in this level of counting with my fingers the degrees of freedom and ignoring any like higher subtleties that might possibly arise. You can use these 6 constraints to impose the 6 gauge conditions that I write here, which basically set the off-diagonal components of the triad to 0. And this choice of gauge completely fixes the internal SU2 gauge freedom, in the sense that after you are in this gauge, there are not any non-trivial rotations of the triad which would preserve the gauge. However, there are left some like residual diffeomorphisms that preserve the diagonal gauge, which if you think of a diffeomorphism as a coordinate transformation, then this residual diffeomorphism looks like this. So it's a transformation where each new coordinate depends only on the single corresponding old coordinate and not on the 2 others. Okay, so this is how it works classically, but as I said, my goal is not to do it classically, but in the quantum theory. So in the quantum theory, what we should do is we represent the gauge conditions by a constraint operator. So this constraint operator should be the quantization of something that classically the vanishing of this something is equivalent to the gauge conditions being satisfied. One way to construct such a thing is to make this so-called master constraint. So you take each of the gauge conditions and you square them and you add all of these together. So Feynman, in the Feynman lectures of physics, at some point he shows how to construct unified theory of all physics. And this you do by taking all the equations of physics that you know, and you move everything to the one side, so the other side is 0. Then you square all of these things and you add them, and then the fundamental law of your unified theory is that this thing such constructed is equal to 0. So the master constraint is somehow very similar to this. Of course, the difference is that what Feynman said, he meant it as a joke. But in loop quantum gravity, this master constraint is a serious idea that people sometimes use. And so I'm now using it here to impose my gauge conditions. And before you can quantize this, you very much like you had to smear the connection and the triad before you could promote them into operators. Also, the master constraint you need to integrate. So the thing which we can quantize is this integral, which is taken over the whole spatial manifold. And here this factor of 1 over determinant is inserted to make sure that the integrand has the correct density weight of 1, because only such things can be properly promoted into loop quantum gravity operators. And this is also useful before quantizing to add and subtract the diagonal components and write the mu constraint like this. So the point of adding and subtracting those things is that now the first term in this, so you do what you always do, you construct some partition of the spatial manifold. In this case, I partition it into cubical cells. These structures you use to approximate the integral in terms of some things like fluxes that correspond to well-defined quantum operators. Because I added, and so at first I had the sum of squares of the off-diagonal components. Then I add 0 in the form of sum of diagonal components squared minus sum of diagonal components, because I want to bring out this term, because this becomes the area operator when I quantize. So this the mu up there is a sum of 6 terms. Here this first piece is a sum of 9 terms. And then here I subtract the 3 extra terms that I added, which were not in the original mu.
But this is not positive difference.
Well, it is because it is identically equal to the first form of mu. So I take this mu and I add ex1 squared plus ey2 squared plus ez3 squared. And at this point, I have the first term here. And then I compensate by subtracting the 3 terms that so yes. So this I quantize it still is a positive definite operator. Yes. Okay, so I quantize it. In particular, I use this. So I assume that I have some background coordinate system, and then there are some surfaces like this, which I use to construct the operator. And here in particular, this A here is the area operator, which is very well known in loop quantum gravity. But in any way, there is now some well-defined quantum operator, and I then have the problem of using it to impose the gauge that I want to have. So what I should do is I should look for states that stick here. So I should look for states that satisfy this equation here, and then the solutions of that are, so in this approach, the solutions of that are the states in which the diagonal gauge is satisfied, and this is basically what it means to do a gauge fixing at the quantum level. So as I said, this structure that I'm deriving here, it already is known in the literature. So following what these people did, I look for solutions such that the graph of the spin network state is a cubical graph. So I mean by this that the edges are aligned with the coordinate directions of my background coordinate system, and then is basically some rectangular lattice on which the state is defined. And since my constraint operator had the structure where it acts independently on every node of the graph, I can just look at one cubical node. But I assume that the part of the state that refers to this node, it has some generic structure like this. Then I can calculate how. So you may think that I'm going too much into the technical details here. The point why I'm showing this in such detail is to explain in what sense I am finding solutions of this constraint, because in the proper mathematical sense, this is a strictly positive operator, and therefore it will not have any exact solutions. So then this is why I show this, is to explain in what sense these states that I claim are.
Given constraints that don't commute, and we know that in quantum theory we cannot simultaneously have states that are simultaneously annihilated by the
Yes.
right? So we consider sum of squares, and then we look for a solution that is minimal, that has minimal eigenvalue.
Yes, minimal, or in some sense small, as I explained, but it is well, but you already know what I'm going to do. So in my sense, it will not be minimal. It's just a small eigenvalue. Well, then you just, because what I will find that they are approximately solutions in the large J sector. So if you want it, so by taking J larger and larger, you can make it arbitrarily small, but not exactly equal to 0. Yeah, but there, at least it.
Maybe that they're not next to the minimum. Okay, the minimum.
Okay, so yeah, but so let me show how it's going. Yes. And this yes. So this maybe I will not explain everything what happens here, because this, like, even though these look like some fancy things like area operator and flux operator, these are basically just angular, they are quantum angular momentum operators mathematically. So this area operator squared is basically the total angular momentum squared of two particles. And this flux operator squared is the square of the Z component. So then yes. Is there a question? I see. Yes, now I think he is muted. It's fine now. Okay, so anyway, if you do all this calculation, you arrive at this after making a specific choice of the state. So the specific choice which you made is that the magnetic quantum numbers at the node are equal to the maximal or minimal possible value. And with this choice, you find that the action of the constraint operator on the state is not exactly zero, but it depends on the -1/2 power of J. So this I mean in the sense that if the state that I put in is a state, the normalized state of norm 1, then the norm of the result is proportional to J to -1/2. And then this means that if in the sector of large J quantum numbers, they don't exactly solve the constraint, but they, well, as I said, not any state exactly solves the constraint. So then this, in some sense, is the closest thing you can find to a solution. And this also, as I already said, this up to some small details, these states that I found here are precisely the states introduced by Alesci and Cianfrani in their model of quantum reduced loop gravity. And these states, they in their work, they called them reduced spin network states. No. Okay, so to me, the interesting thing about these states that I found is explained here. This is my result from a couple of years ago. So when this quantum reduced model was originally introduced, then one of the arguments that the authors made in favor of it is that it's the basic kinematical structure is extremely simple compared to full loop quantum gravity. And then if you are interested in some physical applications, then this approach seems promising because it's easier to do calculations while still being somehow related to the formalism of the full theory. But then they at least in my opinion, they didn't explain very well how this simple structure emerges from the point of view of proper loop quantum gravity. So, for example, in this quantum reduced model, the volume operator acts diagonally on the natural basis states of the Hilbert space. This in comparison to the full theory where on some generic spin network state is not even possible to calculate in analytic form the action of the volume operator. However, what I found is that these simple operators in the reduced model are just nothing but the actual full operators of proper loop quantum gravity just applied to these reduced spin network states that I found from my constraint. The only thing you have to keep in mind that while solving the constraint, you have to assume that you work with large values of the J quantum number. So this O here is some typical operator we might be interested in, like the volume or the Hamiltonian or some such thing. And then if you take this psi reduced spin network state and you apply the operator of the full theory, and first you find a piece which is a state also in the reduced Hilbert space with some coefficient. Then there's another piece which is generically not in the reduced Hilbert space, so the space is not exactly preserved by the action of this operator. However, if you remember the assumption that J is large, then you will find that the coefficient of the first term is large compared to the so to say bad term. And then if you argue that because of this assumption of large J, you can just drop the second piece, then you arrive exactly at the reduced operators that were sort of postulated by Alesci and Cianfrani, but here they are not postulated, but simply obtained by calculation from full loop quantum gravity. And here I have some details of how this result emerges, but I will skip all of this since I see that there's not very much time left. So if you want to see the calculations, there's a paper of mine with where all of this is shown. So then the structure which arises from this approach that I have presented, namely that you first you start with the entire Hilbert space of loop quantum gravity. You construct your constraint operator which imposes the diagonal gauge on the triad and which selects some small sector of the full Hilbert space. So this gives you the Hilbert space of the reduced model. I will come to that, but at this moment the Gauss constraint is not imposed. And in my opinion, it should not be imposed at any point, but if you want that it is imposed, I will show you how it can be done. So then these states, after you find them, they are still elements, so they are a subspace of this full space on this side, which means that you can apply the full operators to these states, and then you find this simple structure here for the elementary operators. So instead of the SU2 multiplication law in the full theory, you basically have a U1 or what looks like a U1 multiplication law for the holonomies. This after dropping the small terms that I was talking about. And the flux operator is essentially diagonal on such states. Yes, so you see, I anticipated your question. First, the Gauss and also the diffeomorphism constraints are not addressed so far. And then to deal with them, there are several options. The first is to do nothing, which to me, this seems like the most correct approach, or it's the one that I would do, and also what people who worked before on this model did in their calculations. The argument being that if you already fixed all the gauge freedom in the Gauss constraint, the diffeomorphism constraint, you also almost completely fixed. Then after this, there shouldn't be any notion of gauge invariance visible anymore in the quantum theory. But since I know that not all people accept this argument, I also present some other possibilities. One is so if you start imposing things with a master constraint, then you always can add more things there, and it's still, at least in principle, an operator whose solutions you can look for. So one way to deal with the Gauss and diff constraints would be to introduce this kind of extended master constraint where these new terms have been added. And then this diffeomorphism term is complicated, and I don't know what these solutions look like. But the Gauss piece is not very difficult to deal with. And what it does, it basically restricts the spins that come next to each other in any given direction. So it constrains them to be equal to each other, just not exactly equal, but equal in this sense that all equalities are in this reduced model. There can be some lower order difference in J between these two. The other possibility especially for the Gauss constraint, is I just mentioned this because there is some other work in the literature, for example, by my colleague Marcin Kisielowski, who in some of his paper considered such states that come from this construction. So it means like a general feature in not only in loop quantum gravity, but elsewhere as well. If you have a generic not gauge invariant state, you can average this with respect to the gauge transformations. So here, this actually is the state not gauge invariant. Then the result of this kind of group averaging is assuming that there is some result and the integral doesn't vanish. Then this result is a state invariant under these gauge transformations. And then if you do this with those reduced spin network states, then there appears this so-called coherent intertwiner with here the 6 normal vectors of the cube. And this, like I said, I just point this out because this is something that other people also have worked with just from a different motivation than how it now emerged here. Then I have one final thing that I want to mention before I finish. That is, of course, if someone puts a question as the title of their slide, you always can confidently guess that the answer is yes. Yes.
So if you integrate by the action those the ambient transformations, then do you obtain terms which make a different magnitude of J or
Of J, no, J is preserved by this operation. So in the state that I put in, there are some fixed J's on each edge. And also the state that comes out, it has fixed J on each edge.
I understand, but the question
So,
is it's norm. There is norm.
It's generally something small.
Right.
Unless the vectors are very, or the J's rather are very specifically chosen.
Right.
But if the norm of the initial state is 1, then generally the norm of the resulting state is exponentially small.
I think the one you are concerned about, like as far as the large J.
Okay, so yeah, so let me
Okay,
explain that.
So you are afraid that if you gauge average, that if you gauge average before eliminating those states which are.
Yeah, so what I'm afraid is that
those smaller case states after gauge everything they are bigger than those.
yes, so this nice splitting of the operator into a leading term and a small term, which I can drop this value before I apply any root average.
Yeah, but it's not preserved by the.
Yes, so if I don't know, it may or may not be preserved, but I don't know. But a priori, it's not guaranteed that after this averaging is applied, that this term still is large compared to the term that I want to min-max. So this is the possible problem of applying this in the reduced model. Okay, so I ask you, because what I did so far is I didn't even guess myself. Alesci and Cianfrani guessed, and then I sort of imitated their guess of the states that satisfy this constraint. So certainly there is not any systematic construction of the full largest possible set of solutions. It seems to me that these states are actually not like you should find some more before you can say that your reduced Hilbert space is complete. Because if you remember I actually didn't emphasize this point very much, but in the action of the operators on the reduced space, it's only the diagonal matrix elements of the holonomy operator that contribute to these leading terms that I want to keep. But if the holonomy operator only has diagonal matrix elements, it means that not only the triad, but also the Ashtekar connection is diagonal in these states. So it somehow seems that too much has been reduced, because classically, if you fix the 6 off-diagonal components of the triad to 0, then these all you can fix. Then the connection is what it is, but there generally is no reason why the off-diagonal components of the connection should vanish. So this is why I'm looking for more solutions, and here I present some like kind of speculative proposal where each full edge of a reduced spin network state is split down the middle. Then as far as my constraint operator is concerned, there's no difference here because the constraint operator only touches the actual 6 valent nodes of the graph and it doesn't see this fake node at all. So this is just some speculation. So far, I've not studied very carefully these states, but they do have some resemblance to some other things that people have considered in full.
In loop quantum gravity, you can split each edge.
Yes, but it's true, like at least before you start thinking of any constraints. Of course, if you insist that in the full theory the Gauss constraint must be satisfied, then there cannot be such a node.
Why?
A two-valent node. The only way so I'm here. There's just so each edge here has some fixed magnetic index.
Oh, they're not much different.
Yes, they are different and they are not summed over.
Okay, in that case.
Yes. So it is from the point of view of the full theory, it looks quite ugly. Okay, so let me now come to the end. So what I did here, I basically re-derived this kinematical structure of quantum reduced loop gravity, which, as I emphasize again, it's already the structure itself was proposed in the literature much before I started working on it. However, this new contribution that or the improvement that I claim to be making is that in my approach to this, it's so what I'm doing and in what way these states and the simple operators arise, it's much more clear and transparent than in the original work of Alesci and Cianfrani. And then, of course, the reason why this is interesting is that it seems to be a somewhat, at least promising approach to the question of investigating the physics of loop quantum gravity, because here you can, and people already have done, you can do some concrete calculations which would be very difficult, if not completely impossible, in the framework of the full theory. So here I mentioned some examples. However, one question that has not been studied, it has basically not been studied at all, is the coupling of matter, well, not just coupling, but some physical applications of matter fields in this quantum reduced setting. So this is something that I have in my list of things that I would like to do. So one of the problems both in the full theory and in this reduced approach is that if you want to treat matter fields in loop quantum gravity, you have to use this so-called polymer representation, because this from the background, from the point of view of background independent quantization, this is the correct thing to use. but the polymer representation looks extremely different from the standard pocket representation that people in normal quantum field theory use. Because of this, it is not very easy to say what or how you would start from loop quantum gravity and arrive at something which would resemble something like a conventional quantum field theory of a quantum field on curved space-time or something. There are some proposals in the full theory of how you could accomplish this, but this being the full theory, they've not been fully completed because you cannot explicitly calculate all the required things. So my hope would be that if you examine the problem here, taking the reduced model instead of the full theory as your supposed theory of quantum gravity, then maybe you can discover something that has not been achieved in the full theory so far. And I stop here. Thank you very much.
So, are there questions from the Zoom audience?
Yeah, I'd like to ask a question.
Yes.
So could you go back to the slide with the diagonal action of the operators on your states?
Do you mean this
The
one?
previous one, I think.
This.
Oh, yeah, this one. Yeah, great. So, what is exactly this class of operators that satisfy this? Because I imagine that if you would take even such an operator and apply it many times to your state, then after sufficiently many applications, this would not be true anymore, because those errors could add up. So, do you have any characterization of the class of operators?
Not any like systematic, not anything that I feel would properly answer your question. But it's true that if you, so this operator might be the Hamiltonian, for example. So if you apply the Hamiltonian 1 million times, then it's not guaranteed that this result is valid anymore.
Yeah, of course, exactly the Hamiltonian was the motivation for this question. Okay, thanks.
But I mean because I haven't studied 1 million actions of the Hamiltonian. You might get lucky, and it somehow happens that the matrix element between the good term, so to say, and the bad term is always sufficiently small that even after many actions, the bad term doesn't get to be very large. But this would be some nice coincidence, but I'm not sure if there is much good reason to expect that actually would happen, anything like that. But it is a thing that should be calculated, and I have just not done such calculations yet.
Okay, thanks.
Are there other questions? Now, what about the audience in the lecture room? You didn't mention the scalar.
Yes, I didn't mention many of the stuff I actually had on my slides, and I still am over time. The scalar constraint is an interesting subject, but it's a different subject, and I don't know how to properly incorporate it into this talk.
Okay. So is there no more questions for the thing to start?